So now we want to talk about current. And current, quite simply, okay, is the flow of charge. So you may be wondering, how do I get charges to flow? Right? How do I actually get charge to flow through something? What does it mean? Right? So the first thing we want to do is define current mathematically. Okay? We want to define current mathematically. And mathematically, we use the symbol I for current. Okay? And mathematically, we say that I is equal to delta Q over delta T, or charge per unit time. Now, a couple of things need mentioned right here. All right, current can flow outside of a circuit, quote unquote, right? Like your typical circuit that you would think of, the circuits in your electronics, the circuits in your household, right? Currents can flow without those types of circuits being set up. But for our purposes, we're almost ubiquitously going to consider circuits as where our charge is going to be flowing. Okay, so a simple circuit, all right, not to jump too far ahead, but a simple circuit is going to look like this. Okay, so here's a basic diagram. Our battery, so when we get to circuit diagrams, our batteries are typically going to look something like this. So if you have in a circuit diagram a long line followed by a short line, or a long line, short line, long line, short line, those are typically the symbols that we use for batteries. All right. Now, you do not ever want to do what I'm doing in this diagram. Okay, I'm just basically hooking the leads of these, the two leads of this battery together with a wire. Okay, but this is what your circuit diagrams are kind of going to look like. And you don't want to do this, because in this particular case, and we'll actually find out why in this lecture why you don't want to do this, but in this case you'll actually fry the battery, if not set it on fire, and that's not a very good thing to do. But the essential point that I want to drive home here is, okay, so a battery has some potential V, right? And we've already defined potential in the last chapter. Potential is potential energy per unit charge, okay? So it's energy per charge. And so the battery is basically your energy source, okay? Now, you don't have to have a battery. There can be other types of circuits. But again, a lot of the circuits that we're going to consider are going to use a battery as their source of energy, okay? And what happens is this battery wants to set up an electric field. Okay, this battery wants to set up an electric field. And if I connect a conducting material, i.e. a wire, to said battery, then if the leads are connected and there's a complete path, then that complete path will have an electric field set up in it. And in this case, the electric field is going to come off of the positive terminal of the battery in that direction, and it'll feed back into the negative terminal of the battery. So I have an electric field. Now here's the essential point, okay? If I have an electric field and I have my wires are made out of what, right? Typically they're made out of things like copper or nickel or iron, highly conductive material. What that means is those materials have electrons in their outermost shells that are susceptible to motion. Okay, so they can be stripped off very, very easily. And they feel this electric field that's set up, and because they're not tightly bound to their nucleus at all, they're free to move. And so what happens is I get charges flowing around the circuit. Now, we define, the convention is current is defined as the flow of positive charge. The flow of positive charge. Now, we know now that that is not what actually happens. We know it's the electrons that flow. Okay, we know it's the electrons that move. But this is the historical convention, so we stick with it. Okay, but we envision positive charges being able to move along this wire, and when the electric field is set up, they move along with the electric field, right? And so we would imagine a flow of positive charge coming off of the positive terminal. And why is the charge going to flow off of the positive terminal? Well, if there are a collection of positive charges near the terminal, once the electric field is set up, those like charges want to get away from the positive plate in the battery. So they're going to be accelerated toward the negative plate, right? And so a crude model of current is just that these charges, these positive charges, flow from the positive terminal to the negative terminal. Now, again, in reality, what's happening is you have a whole bunch of electrons that are actually trying to flow away from the negative terminal, and they enter the positive terminal, right? And then the battery does the work to then push them out the negative terminal again, okay? That's really what the battery does, is provides that energy to push them over that hump, okay? So that is what causes charges to flow in a very crude model, okay? But coming back to here, so what this means is that if I have a way to measure the number of charges that pass a specific point in my circuit, then I can measure that amount of charge and divide that amount by the time it took me to take that measurement, and that is what we define as current. So for example, let's say there was a way, okay, let's say I have a little tiny microscope that can see individual charges flow, and I stick my microscope right in here, okay? So here's a microscope, and, here's my eye, right? So I'm looking at the microscope, and I'm counting the number of charges that pass through this little point per unit time. And so what I might do is set my stopwatch for 10 seconds, count the number of charges, take that total number of charges and divide that by 10 seconds, and that would be my current, okay? So it's just the total amount of charge that passes a specific point in some unit time. Now, in a closed circuit like this, a very simple circuit where I just have wires connected to batteries, and we'll actually put loads in what we call loads in the circuits next chapter. But one immediate consequence of charges flowing in a complete closed loop like this is that the rate of flow has to be the same at all points at the same time, okay? The flow does not necessarily have to stay the same through time. You can have situations where I have a really high amount of current, and then over time that current may die off, it may get smaller. But if I measure the current at any specific point in the circuit, it will always be the same at that particular time. So at a specific time slice, then the current will be the same no matter where I measure it. So I could put my microscope here, I could put my microscope here, I could put my microscope right next to the battery. It doesn't matter. If I take a measurement at the same exact time at any of these points, I'm going to come up with the same answer. Okay, so it does not matter where in a closed circuit you actually put your measuring device, you will actually get the same amount of current in a closed loop. Okay, so what we want to do now is actually introduce the idea of Ohm's Law. Okay, we want to introduce this idea of Ohm's Law. Now remember what I said back here, okay, that if I just put my wires and connect them to the leads of my batteries, then I don't want to do that because it will get hot, potentially catch on fire, all sorts of bad things can happen. Here is why, okay, here is why. If I have something to resist the current, so if something resists the flow of current, Ooh, that's a bad W there. We call this a resistor. Okay, we call this a resistor, or in some cases we call it a load. Okay, and so what a resistor does is it impedes the flow of the charge. Okay, it basically, often circuits are compared with things like water flow, right? Things like water flow. And if you want to think of it that way, then your voltage would either be your pump or allowing water to flow down a hill. The current is the actual rate at which the water would flow, and a resistor would be something like a dam, something to slow down the water or stop the water altogether. Okay, so a resistor is something that just mitigates how much current can flow at a given time. Now, for many materials, not all materials, but many materials, okay, we have found that when we apply modest voltages, things from maybe a few fractions of a volt up through a few hundred volts through that range, many different materials follow this particular type of law, okay? And this says that the resistance of a material is often equal to the amount of potential difference, delta V, applied from the battery or your voltage source, whatever it may be, divided by the amount of current. Okay? And if you think about it, this should make sense, right? If you think about it, this should make sense. If I kind of reverse this equation and I want to measure the current I, then I would get delta V over R. And if you think about it, it makes sense. Why does it make sense? Because I and R are inversely proportional. I and R are inversely proportional. And if you think about it, that should make some sense. The more resistance I have in a circuit, then the less the current should be. Okay? The more resistance I have in the current, the more resistance in a circuit. Then I'm tongue-tied. Let's try that again. The more resistance that you have in a circuit, the less the current will flow. Okay, there we go. Per some given amount of voltage, right? Now, of course, if I hold R constant, then as V increases, my current should increase, right? The bigger a pump I use, the more the water is going to flow, for example. But this is known as Ohm's Law, right? Now, Ohm's Law is also often written as delta V equals IR. So if I know the amount of resistance in a circuit and I know the amount of current in my circuit, that product will give me the voltage of my current, or the voltage of the battery in the circuit. Right? Now, here is why this setup is a really bad idea. Okay, most wires, and maybe let me clean this up just a tad. Most wires that you're going to use to build simple circuits with are extremely good conductors. They're almost perfect conductors, especially if you have a very simple circuit and the wires are not very long. And in that particular case, what we would have is, we would have I is equal to delta V over R. Now again, since they're inversely proportional, if R is big, then I is really small, okay? But on the other hand, if R is really small, right? If it's really small, then I gets really big. I goes up a large amount. And so what that means is my current will approach an infinite value, and that will set things on fire.